Hello, my name is Steven Stefanidis, and I will be presenting an analysis of the traveling salesman problem. So first I'll do a quick introduction. What is the traveling salesman problem? The traveling salesman problem, which I'll call TSP for short, is an optimization problem that asks, if you have a list of cities connected by some mode of transportation, can you find the shortest route that visits each city exactly once and starts and ends at the same city? Now for a couple examples. Imagine you are a salesperson that needs to visit 10 different cities exactly once, leave and return to the same city, and you need to travel the shortest distance possible. Maybe you want to travel the shortest distance to try to save gas or time. This is the most obvious example of TSP and is where the name comes from. The second example is campus tours. Imagine you are a student at a new school and you want to tour the various departments and return to wherever you parked. The school is a rather large campus connected by narrow hallways, bridges, open halls, and pathways outside. If you try to find the shortest route through the school, this is another instance of TSP. And the final example I'll give is the toll roads of Japan. Japan has an extensive network of toll roads. In this picture here, all of the red and green roads are toll roads. So imagine if you are a tourist wanting to visit all the major cities in Japan, return to the same airport, and you want to know which route saves you the most money in tolls. Here I changed the problem from shortest distance to the monetary cost of using the roads. This is okay since the point of TSP is to find a route that minimizes some cost function. This brings us to the formal definition of TSP. Let's look at TSP as a graph problem now. You can see each TSP instance is a weighted graph. And if you didn't know, a weighted graph is a graph where each edge contains a weight that can represent the cost of using that edge. And we usually use complete graphs for convenience because this ensures that there's always at least one possible tour and that each cost between cities is well defined. So in the graph, we can see each vertex is a city, and the weighted edges, where weights represent cost or distance, are the routes. And our main objective is to find the Hamiltonian cycle on this graph that uses the minimum total edge weight. There are two main types of TSP that slightly change the graph setup. We have symmetric and asymmetric. In symmetric TSP, two vertices can only have one edge between them. Therefore, the weight from vertex B to A must match the weight from A to B. This can be modeled with an undirected graph. In an asymmetric TSP, two vertices can have two edges between them with different weights. So the weight from B to A can differ from A to B. This can be modeled with a directed graph. And an example of asymmetric TSP is one-way streets, or if you need to fly from city A to B, which might cost more than flying from B to A. So here are some visuals to show the difference in symmetric versus asymmetric TSP. Notice that in symmetric, each pair of vertices has one edge between them. In an asymmetric, we can have multiple edges, and it's used a directed graph to represent asymmetric TSP. So now that we have discussed the problem setup, let's look into its complexity. Imagine I need to find the shortest path through 5 cities. What should I do? The simplest solution is to try every tour and see which one is the shortest. So to do this, we need to pick a permutation of 5 cities that leads to the lowest cost. This is equivalent to 5 factorial, which is 120, meaning that there are 120 ways to traverse the 5 cities. 120 options is trivial for a computer to check all options with brute force, and even humans could do this with enough time and effort. Now if I ask you to do the same for 20 cities, well, 20 factorial is equal to 2.4 quadrillion, meaning that if we took the same approach that we took on the previous slide, it would require checking 2.4 quadrillion permutations. This is not feasible for computers and definitely not for humans. So this illustrates that TSP has factorial growth, meaning that when given a problem with n vertices, solving TSP naively will require checking 9 factorial tours. Now let's discuss the specifics about its complexity. We measure how difficult a problem is by using asymptotic computational complexity analysis. This is outside the scope of the course, but just know that there are different classes of complexity that problems can have. The P class represents any problem that has a known algorithm to solve it that can run in polynomial time, which means it runs very fast and scales well with large problem sizes. The MP class has problems that can be verified in polynomial time. The MP hard class is the set of problems where there is currently no known polynomial time algorithm to solve it. There are many more classes, but the last one I will mention is MP complete, which only has decision problems, meaning problems with a yes or no solution, where a solution can be verified in polynomial time, but a solution cannot be found in polynomial time. So these type of problems belongs to MP and MP hard. And there's a well-known unsolved problem in math and computer science known as P versus NP that asks the question if the sets P and NP are equivalent. Getting back to TSP, we have two types of TSP problems. There's decision TSP, where we ask a yes or no question, and optimization TSP, where we're asked to find the optimal solution. In decision TSP, the question is there a tour shorter or equal to some length L? This can be easily verified. When given a tour and length L, you can easily add up all the weights of the edges to check if the tour is less than or equal to L. However, it is hard to find such a tour for large graphs. Because the question is easy to verify and hard to solve, it is NP complete. Now if we look at optimization TSP, we ask the question, what is the tour with the shortest distance? This is not NP complete because NP complete only applies to decision problems. And we know that it is hard to find the optimal tour for large graphs. Because this problem is hard and shows factorial growth, it is NP hard. So now just a brief summary of what we've learned so far. Finding optimal tours for TSP is simple for a small amount of cities. However, the problem has factorial growth, meaning that finding an exact solution for many cities is difficult. The optimization variant of TSP is NP hard because there is no known efficient exact algorithm. And when I say exact algorithm, what I mean is a procedure that guarantees to find the optimal solution in some finite amount of time. This brings us to the next section, which we will be looking at some exact methods. The first one is the one that we used in the previous section, brute force. This is the naive approach of trying every permutation of vertices. This effectively tries every possible tour and records the smallest tour. This is highly inefficient and has a big O complexity of n factorial. And big O notation just means that the algorithm takes, at worst, this amount of steps relative to the input size n. But don't worry, there is a better algorithm. Dynamic programming. Dynamic programming, or DP, uses a table of values to record the distance from the starting city to each vertex j using a set of intermediate vertices. The goal is to build a final solution by using local optimal solutions. This algorithm has been shown to be big O of n squared times 2 to the n, which looks large, but is actually significantly faster than n factorial for large n. However, due to storing a table of values, DP requires a lot more space than brute force, which only needs to store the graph. Now here's a table comparing brute force and DP. We can see with 5 and 6 cities, brute force actually outperforms dynamic programming. However, when we reach 8 cities, this is when brute force becomes much slower than dynamic programming. And by the time we have n equal to 10 cities, brute force is really slow compared to dynamic programming. So our conclusion is that brute force algorithms become much slower than DP for any TSP instance with 8 cities or more. Now I'll talk about integer programming. In class we looked at continuous linear programming, where decision variables can be fractional. Integer linear programming, or ILP, introduces the constraint that decision variables must be whole integers. And believe it or not, this one constraint makes ILPs much harder to solve than LPs in general. In fact, LPs are in class P because there are methods other than simplex that solves them in polynomial time, and ILPs are believed to be MP hard. The reason that I mention integer programming is that TSP has been formulated into an integer program by Miller-Tucker-Zemlin and Danzig-Fulkerson-Johnson. This image below is a DFJ formulation, where Cij is the distance between vertex I and j, Xij is the decision if we actually use the edge, and we use 1 to mean that we use the edge, or 0 to mean that we do not use the edge. The top is the objective function that we try to minimize, where we need to optimize Cij, Xij for every pair of vertices. The next two rows ensure that each city has one incoming edge and one outgoing edge. And the last row is complicated, but it basically forbids having multiple cycles or subtours, and forces the final solution to be one large tour. LP solving software has been made that can solve large-scale problems efficiently on average with a worst-case exponential time. So even though they have been shown to be more efficient than DP or brute force, they still are not a polynomial time algorithm because there's a worst-case exponential time. The world record for largest TSP instance solved with exact methods was done by Applegate, Bixby, Kvatal, and Cook using the solver QSOPT from the University of Waterloo, and they solved 85,900 cities. The world record used a branch and cut algorithm, but time complexity analysis is difficult because it is not a deterministic algorithm like brute force or DP. In the previous section, we looked at algorithms that are guaranteed to find the right answer eventually. Next, we have approximation methods which are not guaranteed to find the optimal solutions, but sometimes they can be guaranteed to be within a certain distance from the optimal solution, though this is not always the case. The advantage of these is that they can be much faster to run than exact methods. The first one we'll see is nearest neighbor, or NN for short. This is a greedy algorithm that always makes the local optimal choice. The method says, at each city, choose the nearest city that has not yet been visited, or the city with the shortest distance that has not yet been visited. And this can result in different solutions depending on which city you start from. It has been shown to be 25% longer than the true shortest path on average. However, many TSP instances have been created that lead to NN picking the worst possible tour, which is true for both the asymmetric and symmetric TSP problems. So NN works on average, but there are some TSP problems that it does not work well for at all. And then we have the Christophanides algorithm. This takes advantage of the triangle inequality that states for every 3 vertices u, v, and x, it is necessary that the weight of uv plus the weight of v to x is greater than or equal to the weight from u to x. So if we have a graph that meets this inequality, we can do the following. We find a minimum spanning tree T of G. We let O be the set of odd degree vertices. We make a subgraph that only uses O and find a perfect matching M with the minimum weight. And then we combine the minimal spanning tree T with this matching to make a new graph H, where each vertex is guaranteed to have an even degree. We can then find an Euler tour in H, and we know that H has an Euler tour because it only has even degrees. After we find the tour, we remove any duplicated vertices in the tour to shortcut past them for the Hamiltonian tour. This algorithm guarantees a solution that will be within a factor of 3/2 from the optimal length. However, it only works for certain instances of symmetric TSP that obey the triangle inequality. So just a quick walkthrough of the algorithm here. This is the TSP problem we've been asked to solve, and you can analyze the edges to see that it does obey the triangle inequality and is symmetric. Next we find the minimum spanning tree, and a tree is this is the tree that connects all vertices together with the minimum weight cost. Then we need to calculate all degrees and create the set O with odd degree vertices. So this one will be pruned because it has 4 degrees, which is even. And then we form a subgraph with only vertices from O. Then we find the minimum weight perfect matching M using O. And finally, we combine M, this one here, with the original tree that we had to create this new graph where each vertex has an even degree. Then we find an Eulerian tour. In this case, we start from A, go to B, C, A, D, E, A. And since we visit A more than once, we're going to cut out this A. So this is our final Hamiltonian tour that skips past A and ends up forming a Hamiltonian tour. The last approximate method I will talk about is self-organizing maps. This is an artificial intelligence method. It is an unsupervised neural network that creates characteristic vectors to represent high-dimensional data in low-dimensional space. It organizes neurons into a fixed map. Usually we use 2D grids, but in this problem we use a circle. And if you see this animation on the left, the circle acts as an elastic band that forms a near optimal tour over time. There is no guaranteed for this optimal solution, or there's no guaranteed for this solution to be close to the optimal solution. But this method can be very fast for a large amount of cities. And this method is not as practical as the previous ones, but is more so an interesting approach to solving TSP. And I will now talk about some real-life applications of TSP. Logistics. This is the main most obvious application. For example, making a school bus route that picks up children in a school district. More recent applications involve the scheduling of service calls at cable firms, the delivery of meals to homebound persons, the scheduling of stacker cranes in warehouse, the routing of trucks for parcel post pickup, and a lot of other problems. We also have circuit board design, where components on a printed circuit board must be connected with traces, and we want the shortest total wiring used. And then we have travel itineraries. So this is a personal example where I wanted to plan an amusement park road trip across the USA. In this case, the amusement parks would be the cities, and the weights of the edges are the ETAs computed by Google Maps. And then finally we have robotics, where TSP can be used for controlling a robot's pathfinding and decision making. In conclusion, traveling salesman problem is a highly relevant optimization problem that is easy to understand, but difficult for computers to solve efficiently. We have a lot of exact methods that can get an optimal solution, but they may take a long time to run. And we also have a lot of approximate methods that are generally much faster than exact methods, but they do not guarantee optimal solutions. Thank you for listening to my presentation. Here are the references I used. The top 3 are Wikipedia articles, and the University of Waterloo had the QSOPT solver information, and also some applications that I quoted. on this page. And this is a article that talks about self-organizing maps and also had that animation that I used. And here's some image sources.